Okay, welcome to the class. So, this is kind of a unique kind of field theory class, because I do not work on quantum field theory, but I work on classical field theory, and the tools are roughly the same. Of course, there are a lot of differences. So, I thought I will try to mix all together and see the similarities and dissimilarities, and also look at what are the unsolved problems. Okay, if you work on particle physics field theory, then you do not really know what are the issues is with the turbulence field theory and vice versa. So, this course to best of my abilities I am going to contrast various fields, and there are lots of unsolved problems, and that is what I will try to highlight. Okay. So, you can see that the scope of this course is very wide: classical, quantum, equilibrium and non-equilibrium. This aspect, equilibrium and non-equilibrium, is not emphasized significantly in most field theory courses. I can just tell that many body physics as well as most of quantum field theory of particle physics, they focus on equilibrium field theory. They do not tell it explicitly, but it is equilibrium field theory. But turbulence is a non-equilibrium field theory, and also there are many dynamical systems in statistical physics for which we use non-equilibrium field theory. Okay. There are lots of issues with this aspect, and that is what I will cover significantly on this non-equilibrium field theory. Okay. Okay, so you need to look at that screen if you want to see the notes, otherwise yeah. So okay, so in this introductory lecture I am going to tell you the overview, then we will get into specific details. So, this field theory course is about, okay, I am going to cover all of it, okay, but not in depth, but there is no time to cover in depth. This will require 4 courses. So, we will do in one course. So, you may know that the field theory is the most fundamental physical theory of nature. It includes quantum theory and relativity, statistical physics, all put together. In fact, it has been built very nicely by lots of experts. So, you will see some names in the course like Feynman, Dirac, then Wilson, and then in classical field theory we have stalwarts like Kregnan, Kolmogorov has contributed. Okay. So, it is a basically culmination, the peak of understanding, and combined, it is all combined, but do not assume that it is all solved. Okay. For example, this one field theory essentially is perturbative. Most of the calculations are perturbative, like we do in Taylor series, we do term by term. So, there are very few exact solutions, okay, very few exact solutions. So, perturbation, is it valid, not valid? If it is not valid, then what do we do? So, there are issues which are still a problem, I mean still unsolved. So, the fields, as I said, we can classify in 4 main categories like particle and nuclear physics, condensed matter physics, which is like many body physics is called. Okay. Particle physics also is many body physics, but there are names given. I mean many body physics is first basically condensed matter physics like semiconductors, metals, liquids. So, that is condensed matter physics. Then statistical field theory, that is for phase transitions, fluctuations. So, that is statistical field theory. It is mostly connection between basically stat mech. Okay. So, the non-equilibrium stat mech is in statistical field theory, with phase transition being one major theme, and turbulence, and but this is one general topic. It includes other systems which I am going to cover later part of the course, like coarsening, like pattern formation. We will do some of the field theory for that. Okay. So, now let us look at specifics of these 4 topics. Okay. What is field theory, how field theory comes into these 4 topics. So, okay, before that okay, let me, so in fields, so like most people have done quantum mechanics course, in fact all of you have done quantum mechanics course, statistical physics course. So, in quantum mechanics and classical physics we deal with particles. Okay. So, Schrodinger equation for particle in a box or electron in a hydrogen atom. Okay. So, this is particle, but we have electromagnetic field as well, no. So, electromagnetic field should be quantized, because everything is supposed to be quantized. So, when you quantize electromagnetic field we get photons. Okay. So, electrons interacts with photons as particles. So, this in electron itself can is in fact there is no single particle. Okay. That is what this my next point is, there is no single particle in quantum field theory. Electron, okay, just imagine electron will generate electric field, right. So, the electric field will generate photons, well basically photons will is quantum version of electric field, right, and these photons will generate positron electron pairs and in fact other particles too. So, this photon P photon will generate electrons and positons E plus and E minus. So, it turns out there is a huge number of particles if we start with a single electron. So, that is why it is called many body physics. Okay. In nature there is no single particle, each single particle will generate fields and that in general will create particles. So, field theory is combination of particles and fields. Okay, it is a comprehensive description, that is why it is really in fact is fascinating description, very successful one. You can imagine that because of this what I just made a little sketch here, this particle number is not conserved, right, because they keep generating and destroying particles, okay, and mass is not conserved. Okay. So, like photon if you think of as energy then it will create mass and vice versa. So, classical physics assumptions are not is destroyed yet. Single particle theory is incorrect. It is just said we can't have one electron and write down the electric field per electron, that is not possible in field theory. In fact, in nature it is not possible. What we do it is a good approximation if a charge is very big, okay, very large charge. So, single particle like we do particle in a box, electron in hydrogen atom, these are to be modified. In fact, you may know that in quantum electrodynamics so whatever we do in classical physics like magnetic electron in a magnetic field, no, there is a Zeeman effect and there is a correction because of quantum field theory, and that is what Feynman, Tomonaga, Swinger they calculated it and they found the experiment and theory matches very well, and that supposed to matches in 10 digits of accuracy, and that is what won them a Nobel Prize. So, that is basically field theory effect, okay, many particle effect. Okay. So, so I hope you understand. I mean this is reasonably difficult, it is not easy, okay, but we will get a flavor of it, okay, and you can dig deeper if you are interested. So, in particle physics QFT combines relativity and quantum mechanics. In fact, as I said field theory is used in many fields, okay. So, I am just telling you what are the main, well in one slide I can't cover all of it, but I will just tell you gist of what we do in particle physics, and we will cover more details in the course. Without this we can't cover field theory, okay, particle physics has to be covered. So, QFT quantum field theory is a short form of quantum field theory combines relativity and quantum mechanics, okay. So, E equal to mc squared, and that is definitely there as a one of the ingredient of field theory, and provides a consistent theory for particles and fields, okay. Particles can be created and destroyed, as I said that is what field theory is about. So, QFT has predicted and explained many phenomena, unification of forces. So, we may know that nature has 4 fundamental forces: gravity, electromagnetic, weak nuclear and strong nuclear. it turns out for 3 of them have been combined in a single theory, okay, except gravity. So, that is called unification, and it is a big achievement, okay, and people are trying to combine gravity, okay, and not succeeded so far, but this is one major thrust arising out of field theory. Quarks is a prediction from field theory, Higgs boson, which has become very hot topic, or after the Nobel Prize came several years before, renormalization, okay. Some of it we will do in the course, not unification, not quarks, but Higgs I will cover in a broad way, and renormalization. This is renormalization is a general phenomena in field theory, in particle physics. The charge of a particle is not constant. The charge of an electron, what we say is 1.6 10 power minus 19 coulomb, that is the effective charge at a low energy. If you increase, if you probe with a higher energy, I mean if you take a charged particle and you probe deeper, then you will experience larger electric charge. So, electric charge what we quote is not the basic charge of electron. In fact, supposed to be charge is very large, infinite charge, but it differs because of this many particle effect, we observe this effective charge, similarly mass of electron. So, we will see some of it, this is called renormalization, okay. So, charge of electron depends on the energy of the probe. In fact, it is quite easy to see if you have electron here which has infinite charge, okay, but electron will create electromagnetic field, and then we will have lot of positron electron pairs. So, electron will attract the positron closer and repel the electron further. So, E plus will come closer in this particle and E minus will be far away. So, we will have lot of E plus in the neighborhood, okay, that will shield this real charge of the electron. So, real charge of the electron is shielded by this virtual particles surrounding the electrons. You understand what I am saying? So, that is why if you are far away, I mean if you are somewhere here, then you are not seeing one electron, okay, please remember you are not seeing one electron, you are seeing lots of particles collectively from far, and so it is shielded by this lot of positrons, and that is why you see less charge, not infinite charge, and depends. So, the charge will depend on how far you are from the source. If you are too far away, then you will see less. If you are too close, then you see more, okay, and this is called renormalization. Renorm means you are normalizing charge with energy. Energy is proportional to the distance, right, well higher energy less distance, okay, inversely proportional, right. So, that is what is renormalization about, which again Feynman, these are the pioneers for this, but we will see that same phenomena occurs in condensed matter physics, phase transitions, turbulence. So, this is what, this will be one major theme of our course, okay. So, that is what, when you are far away, then the effective charge is that 1.6 10 power minus 19 coulomb, okay, if you are too far away, okay. So, field theory is in fact very beautiful theory, and it is the most fundamental theory, okay, and it is the basically fundamental theory for all parts of physics, particle, condensed matter physics, stat-mech. So, key issues is particles and fields are quantized. Fields are quantized, you know, particle being quantized, everybody is aware of it, but field being quantized, you people heard about it, but we will show you how it is done, okay. Like electromagnetic field, we quantize it, then we get photons, okay. Same thing happens for other fields like, okay, Higgs or nuclear, but I am not going to deal too much with that. We will just stick to many-body and electromagnetism, okay. This course has a broad agenda, and I am not also expert of particle physics, so I should not claim any of those stuff, but you will get a broad picture, which is I think important. Particle number and mass is not constant, single particle theory is not correct. So, what I just said here, that the electron creates a field, electromagnetic field, and that in turn will create particles, like photons is a electromagnetic field, and that will create virtual positron and electron pairs, right. In fact, other pairs too. Photon will create quarks and antiquarks also if you give enough energy, okay. And the electron will attract the positive charges and repel the negative charges. So, I think that is the question. I hope so in fact, you must have done this, no, the effective charge, effective electric field or potential is e to power, it is not 1 over r, e to the power minus alpha r by r. In plasma physics you seen this potential? No, Vimal. So, we have big charge, but there are a lot of positive and negative charges. Okay. Plasma has positive negative charges. So, the charge is plus q. So, what is it going to do? It is going to attract the negative charges and repel the positive charges. So, you are not going to see plus q, you will see less reduced charge, and that is why potential is not 1 over r for this q by r, but q times exponential minus alpha r is called shielding, Debye shielding. Now, look, this course you have to be okay, you have to be taking things from everywhere. If I just try to derive Debye shielding here, course is gone, okay. So, some of it, okay, I am not asking you to go back to plasma physics and read in detail, it is go to Wikipedia and look at Debye shielding, okay. Exactly what happens in Debye shielding happens for QED, quantum electrodynamics, okay. Everyone, is it clear? So, Debye shielding you should just look at it, same phenomena. In fact, this is very generic, this is called shielding effect, and particle physics, this was where I was. So, I just said that in fact, this is what mostly is highlighted, there are lot of Nobel prizes were given for this, which are important. I mean, I would say that these are extremely difficult problems which were solved by lots of very great faces, including Feynman. So, Tomonaga, Stringer, Salam, Weinberg, okay, all Dirac was, I think he is the first person whom we can give credit. The field theory starts from Dirac, okay. Creation annihilation operator, I think we can possibly tell Dirac starts it, okay. Okay, this was where I was. So, any questions on this? So, the next topic is many body physics, condensed matter, okay. Condensed matter is broad field, no, I mean where this Ashcroft and Mermin, that book, superconductivity, metals, liquids, okay. So, so basically you start condensed matter physics by band theory, you know, chronic Penning model, and you describe band. So, this is single particle theory. So, chronic Penning model is the electron in a set of delta potentials, periodic delta potential, and you get bands, no problem, but that is not enough. Huh? So, the like superconductivity cannot be explained by naturally by this theory. So, we need many body physics. In fact, metals, forget about superconductivity, metal itself requires many body physics. This is again creation annihilation operators, more electrons, interactions, okay. So, some of it we will cover in the course broadly again. So, metals in electron fluid, this is Landau's theory, okay. Landau's theory of electron liquid, superfluidity, superconductivity. So, this requires many body, okay. Bose-Einstein condensate, which has become very important nowadays, that is many body. Of course, some of it we approximate, like superconductivity is we deal with a effective wave function, okay. So, that is many particle wave function. So, you will get gist of it, what is meant by many particle wave function, okay. And why many particle, you see, as I said, we are dealing with many particles, many body is many particle. So, you will see that is in fact very interesting, very nice theory. Band structure fundamentally we get from chronic Penning, but there are modifications. So, typically we assume equilibrium nature. Okay. I will describe what I meant by equilibrium when we deal with it. So, my interest in field theory is equilibrium, non-equilibrium. So, I have been looking at what are the new assumptions are to be made, okay, and that is where I had to see which assumptions are not going to work, which assumptions are going to work. Okay, statistical field theory. This is a really important aspect. This again has many Nobel prizes. So, statistical mechanics all of you are aware of, no, I mean is thermodynamics is explained formally using statistical physics, like you can derive PVs and RT, ideal gas, but ideal gas is simple, but if you go to phase transitions from ferromagnet from paramagnet to ferromagnet, then those in fact assumptions of the thermodynamics does not work, the standard thermodynamics does not work. There are fluctuations which are pretty large, and that requires field theory. Okay. So, one important point, how do you connect this quantum field theory with StatMech? In fact, this is very nice connection. Path integral of quantum field theory is mapped to partition function. Okay. Now, right now it looks like word for you or sentence for you. I will show the connection. Okay. There is a beautiful connection. So, all the formalism of quantum field theory can be ported to StatMech. Okay, because of this connection, you know how to solve the path integral or you have the formulas, then we do not need to do much work, you just have to translate it to StatMech. Okay, and using that we can derive a lot of interesting stuff. Okay, many body tools are employed here. Phase transition is one important thing, like the Wilson name is Wilson, very important contribution. Okay, we will cover that in the class. Thermodynamics does not work. Okay, I mean for phase transition it does not work. Spin chains, many electron systems, there are a lot of interest right now. Okay, in this quantum phase transition. Okay, that is another many body problem, but we are not going to deal with that in this course. Okay. Typical equilibrium systems, but there are non-equilibrium systems also have been studied in major details. I mean, a lot of people have worked on it. So, dynamical field theory. So, dynamical means time dependent dynamics, no, statics versus dynamics. So, dynamical means time dependent. So, turbulence is one such phenomena. Okay. Here we have to it is not in equilibrium. Okay. Now, so I can just say this following. So there is something called detailed balance. So what is detailed balance? So there are lots of people in a room, but they are not going to, nobody is going to be richer than other person, everybody has equal money. Of course they need to transact. So somebody has some toffee, some other guy has some other sweets. So they will transact, but nobody will get, basically somebody x gives something, same value will be given by either the same x to y, y to x, or x z to x. So in this interaction, like in this room thermodynamics, well not in this room. Okay. So in thermodynamics this particle, no particle has more, well particle in general, every particle has equal energy, right, that is what we assume, half mv square is kBt. In this collision process, each of them on the whole, sometimes they lose, sometimes they gain, but on the whole energy remains constant. But that does not happen in turbulence. Turbulence, some of them are richer than the others. We have large scale structures. So large scale structures are more energy than small scale structures. If a large scale structures give energy to small scale structures. Okay. So that means somebody is giving to somebody else net, and some, in fact large scale structures are fed energy by some other source. So there is a net energy transfer in this system, in turbulence. unlike thermodynamics where there is no net energy transfer. Everybody is equally rich, or it's like communism system. Okay, this is like everybody is equal in that. In lot of natural systems, it is not the case. There are hierarchy, there is a multi-scale description, there is a energy transfer. So, energy transfer means detailed balance is broken, there is no balance, okay. It is non-equilibrium, there is transfer, in fact, there is huge transfer. So, that is what is called time dependence, okay. And there frequency and time plays a big role. The energy transfers are to be computed by looking at that aspect of physics, okay. So, in fact, equilibrium I am going to show you that Green's function, which is a very important object for field theory, and correlation function, they are equal, but in non-equilibrium field theory they are not equal, and more complex computation compared to equilibrium ones, many assumptions, still unsolved issues. These are some examples, okay, like turbulence, KPZ, Kadar, Parisi, Zhang, okay. The KPZ is short form for these three people, time dependent, Ginzburg, Landau, Kahn, Hilliard. Coarsening is pattern formation, okay, essentially. So, if you see that in nature a lot of pattern formation can be explained using this equation, coarsening equation, okay. So, theme of the course is, as I said, broad agenda covering many fields. Comparative mode, I mean basically comparative study of this thing, highlight equilibrium non-equilibrium aspect, which I gave one example, highlight unsolved issues, we will avoid detailed calculations. I will not, I mean if I get into detailed calculation, which some of it I can do, it is just going to be 3 lectures, okay, and then we will not be able to see the broad picture. So, this course is basically broad picture, okay, that is my objective for this course. So, we are not going to do detailed Feynman diagrams for a phenomena. I am just going to say that, okay, this is how it is done and this is the result. So, renormalization of charge, I will broadly tell you how it is done and then I will just state the formula, okay, that is what we will do. So, the charge renormalization is something like 3 lectures, okay, I mean it is 4-hour class. Okay, this syllabus which I shared with you in that first handout, okay. So, quantum field theory, SFT is statistical field theory, then quantum field theory 2, which includes Higgs mechanism, mass renormalization, you know, I just said, and then we will do dynamical field theory, okay. So, turbulence. So, we will cover these aspects in a broad framework. So, as I said, we have one canvas, I am going to put pictures of various aspects of field theory, and you will be basically seeing how the connections, and is your interest now after that, I mean if you are interested in this field, then you find what you like and then you explore more. Okay, references, I think it is important. So, as I said, this is a very broad course. So, we can't find one book to cover one book that will cover all these aspects, but this book I really find to be interesting, quantum field theory for gifted amateur. That's like the title is itself is pretty interesting. So, these authors they say this, that okay, look, field theory is very nice, interesting, beautiful, and they want to give exposure to a person who is not trained in field theory or who is not practicing field theory, not a particle physicist or a condensed matter physicist. So, it has almost all the topics included. My sequence in this course will be different than this book, but I am going to cover half of this book, okay. The standard book is Peskin and Schroeder, okay. This particle physicist, these two are particle physicists. So, in particle physics, I think this is a very standard textbook. Some of the thing which I am going to use, well, I mean this is not really, but some of thing I have done in the chapter 12 of this book, I have field theory done there for turbulence. I will take material from there. In turbulence, this is the standard. Well, I think this is one of the best books by Mecom on who talks about turbulence, I mean field theory of turbulence. The person who worked on this is Krecknen, but Krecknen's papers are very hard to read. Okay. So, Krecknen is the person who pioneered field theory in turbulence. There are various articles which I will use on the way.